Okay, in lesson 26 we're going to look at the beauty of LDA, which stands for lithium diisopropylamine, and I'll show you how to make that in just a minute. But the cool thing about lithium diisopropylamine, LDA, is that it's very selective for grabbing hydrogen. It's a strong base. It's very good at grabbing hydrogens that are at the alpha position to a carbonyl. And so they're very good at making enolates. And as we saw last time, with bromine or chlorine, this enolate can come and pull its electrons down and go over. And so we can actually do this with an alkyl halide as well and get an R group at the alpha position of a carbonyl. Now, LDA is a very strong base. I'm going to show you how to do that, make that in just a second. But essentially, you have to be very careful in using any other type of base, which obviously can work as well, but you'll end up with a mixture of products because LDA is very good at pulling just one of those off, and it's just not going to be as messy as you might have with other types of things. So, to make LDA, we start with diisopropylamine and add that N-butyl lithium that I told you about that could spark fire. That's kind of dangerous. You have to watch out for. And you do this at very cold temperatures, and you form this guy in situ. And what that means is that you actually form that in the reaction vessel, and then you start adding your other stuff to that LDA. Okay. If you have an asymmetric ketone, you could actually form two different products, right? You could end up having this R group come over here due to an abstraction of a hydrogen here. Or you could have a hydrogen removed from over here, giving you an R group here. Before we look at any of this stuff, it makes sense that these are more accessible. Therefore, this is easier to grab. So at low temperatures, it grabs the easiest, most accessible thing that there is. It grabs this hydrogen, which gives you an R group over here. That's the fastest thing that's formed. That's the kinetic product. At higher temperatures, the most stable product will be formed, as we've seen earlier in the semester, right? So if that happens, then this would be the preferred hydrogen to remove, even though it's a little bit more hindered. And that's partially because the enolate itself is more stable, because you have then a more substituted double bond, etc., etc. So this would be the thermodynamic product. Okay, so at higher temperatures, and at this point we're kind of talking about like room temperature as being a higher temperature, then you'll get the thermodynamic product. Otherwise, you'll end up getting the kinetic product if it's run really cold temperatures. So as you see, we're starting at negative 78. Just keep it that way if you want to end up getting the kinetic product usually. Okay. We can also do some really cool stuff with enamines. Remember how we talked about those before? When you have a ketone or aldehyde along with some secondary amine and trace acid, you end up making this enamine. Well, if now you put in an alkyl halide into the reaction mixture, once you make this enamine, instead of it going and grabbing hydrogen from a water, this can come down and come over and do some type of substitution reaction, giving you your R right there as well. And if you recall, once you just add HCl and H2O, the enamine is in equilibrium. It will go back to that C-double-O bond. The advantage here is that you get monoalkylated aldehydes and ketones without having to use LDA. Notice there's no base here really at all. It's all in acidic conditions. Well, that becomes very important if you're trying to work with a compound that has another area in it that may be base sensitive. Okay. Other cool things that enamines can do is that it can actually work with something like this. So that's the alpha beta unsaturated ketone or aldehyde, right? As these electrons come down, these would come over, and bam, he's going to attach right there, right here. And then again, with HCl and water, you could end up making the two guys, both carbonyls. Now notice there's two carbons in between this. That's important because later we're going to look at things that are just one carbon in between it. Another thing they can do is as these come down, this would come in and again replace that chlorine. So we have this type of structure again. And after following this with HCl and water, we then get this guy. There's only one carbon in between that. You probably want to try to work through the synthesis on your own, or this mechanism on your own, because it's not exactly as easy as I'm making it look. But I think that you should try to propose a mechanism, and I'd be happy to look over that if possible, or if you want to send it to me, it's fine. Okay. Here's where things get a little bit more complicated. And we're approaching several types of reactions like this that are going to get, it's not that they're difficult, it's just that they become larger or bigger molecules, and so they can sort of be tricky for that reason alone. So here we have an alpha-beta unsaturated aldehyde, as well as a diester with one carbon in the middle. Well, that means that this hydrogen, either of those hydrogens that are in there, are relatively acidic. So with a base present, we can end up getting this type of structure. You can already tell that this double bond has gone away, right? Well, here's what it does. So in this case, I'm going to use just base OH minus. If you're doing something up here, you would want to use OCH3, because this is the same thing as what your base is, because these can exchange. So keep that in mind. So here we have a base that comes and abstracts the hydrogen. Electrons go back to that carbon. So we have a carbanion. This is only existent, recall, because you have resonance structures here. Well, this guy is going to come in and attack at the beta carbon. Electrons go up and up, just like we saw this before, right? We saw this type of structure before. This is going to be a weak base coming in, up and up. And then as it falls back down, the double bond goes in search of something to bond with. And if there's water present, it will find that, and electrons go back. So, that should not be there. So there is no double bond here in this final product. Okay? And I did give two different examples here, so please be aware of that. Okay. Next we have aldol additions. And this involves two of the same molecule coming together, at least at first. Next lesson we're going to look at two different types of things coming together. But first, we've got two of the same thing coming together. So you have to be careful when you're putting your stoichiometry together before you actually attempt to do this reaction. In the presence of base, I'm going to cover things up here. You can see that this is the same thing that we started with. 1, 2, 3, 4, 5 carbons and an oxygen, right? 1, 2, 3, 4, 5 carbons and an oxygen. Okay. Now I'm going to cover this side up. 1, 2, 3, 4, 5 carbons. And now that oxygen's just been converted to OH. Wow, that actually isn't really so bad. Just have to figure out how to link them together. Okay, so here's how we do the mechanism, because that'll tell us how we link things together. We have a base coming to extract an alpha hydrogen. Electrons go back, giving you the carbene. We've now got a great nucleophile, and that nucleophile attacks the electrophile. In this case, obviously, is going to be the carbon. Electrons go up. If this is run in presence of water, then bam, he just goes over and grabs a hydrogen and then reforms the base so that he can go attach another one. So this is an equilibrium. Depending on what your pH is, you would obviously acidify this, or as you're finishing up the reaction to clean it up. But this can be, these can start to get a little bit tricky when you look at synthesis as to which one do you use, right? So you just have to think your way through this. But in this case, what we have is we have a carbonyl, carbon, carbon, OH. So that means that this would be the alpha beta position. We call this a beta hydroxy aldehyde or ketone. usually ketone, in order to make it actually work this way. So that's basically what you do for an aldol reaction. The Michael reaction is instead adding an R group in between those, right? Okay, just want to make sure that we're clear. On to the next and more complicated on 27. Thank you.